In this video, we're going to talk about the Poisson approximation to the binomial distribution. So recall that, let's recall the binomial distribution first. So the binomial distribution, and these are two discrete distributions. The binomial distribution is when one way to think about what's going on is you perform an experiment n times, and each trial, so each time you do the experiment, has probability p of success. So it could be that you're doing the same trial over and over and over. So for instance, you could be flipping a coin, and if it's a fair coin, then the probability p is 1/2, so you flip a coin n times. And you're looking at the number of successes. The distribution of the number of successes. So let's call that S, okay, for the number of successes. Well, this has the property that the probability that S is k, so k is some integer from 0 to n, right? You can either have 0 successes, 1 success, up to n successes. Well, what's the answer? What's the probability? Well, if you have k successes out of n, then you have n minus k failures. So you have n trials, and you have to pick exactly k of them to be successes. So there are n choose k ways to do that. And then for each of those n choose k possibilities, so you have k successes and n minus k failures, the probability, since these are each trial has probability p of success, so then the probability of those k successes is going to be p to the k, and then the probability of those n minus k failures is 1 minus p to the n minus k. So this is for k from 0 to n. And when we have something like this, it's a distribution where the probability, so you have a random variable, say s, where p of s equals k is that, we say that S has a binomial distribution. So we say that S has a binomial distribution with parameters n and p. Okay, so that's the binomial distribution. So any random variable, any discrete random variable with this probability distribution is called, we say that has the binomial distribution with parameters n and p. Okay. So then we have the Poisson distribution. And the Poisson distribution is another discrete probability distribution. So we say that x, a random variable, discrete random variable, has a Poisson distribution with parameter lambda. So the abbreviation is x is the squiggle, Poisson lambda, so that's how we write it, if the probability that x is k is e to the minus lambda, lambda to the k over k factorial. So this is for k equals 0, 1, 2, and so on. This goes on forever, right? So we don't have like n. Okay, we're not doing something n times. This is just a discrete probability distribution, and the probability that x is k is this. So for instance, the probability, if you have a random variable with a Poisson distribution, then the probability that x is 0 is e to the minus lambda, right? And then the probability that x is 1 is e to the minus lambda times lambda over 1. Okay, and then the probability that x is 2 is e to the minus lambda times lambda squared over 2 factorial, and so on. And here lambda is greater than 0. Okay, and one can check that this is a probability distribution. Let's check that this is in fact a probability distribution. So this is a probability, this p of x equals k is a probability function. Well, what we need to check is we need to check that when you sum all the possibilities of k, of these p of x equals k, then you get 1, right? That's what you need to have happen to be a probability function. So what is the sum? Well, you get that. Then you can move the e to the minus lambda out. So you get the sum of lambda to k over k factorial from k equals 0 to infinity. Well, what's that? That's e to the lambda, right? That's equal to e to the lambda. Because remember, we have this power series. So just in case you're not sure, we have this power series expansion of e to the x, which is the summation x to the k over k factorial from 0 to infinity. So you get e to the minus lambda times e to the lambda, and that is equal to 1, which is what we wanted to show. All right, so this is a probability function, and it turns out that there's a relationship between these two distributions, the binomial distribution and the Poisson distribution. So that's in the following theorem. So the theorem is, this is often called the Poisson approximation to the binomial. So in other words, we're using the Poisson distribution to approximate the binomial distribution. And the theorem is, so suppose that you have for each n a random variable Sn, and this has a binomial distribution with parameters n and p sub n. Okay, so S1 has a binomial distribution with parameter 1 and p sub 1. So p sub 1 is just the name for the it's the number that we give for the probability of success. And then S sub 2 has a binomial distribution with parameters 2 and p sub 2. So in other words, S sub k, or well, let's do S sub n. You're thinking of performing an experiment n times with probability p sub n of success. Right. Okay. Then it turns out that if p sub n goes to 0, so as n goes off to infinity, the probability tends to 0. The probability of success goes to 0. And n times p sub n approaches lambda as n goes to infinity. Then the probability that S sub n is equal to k as n goes to infinity approaches e to the minus lambda times lambda to the k over k factorial. Which is a Poisson distribution. So one way to think about what this is saying is if we have a large number of independent events with small probability then the number that occur has approximately a Poisson distribution. Okay. Or another way of thinking about this is if, so what we can think is if Sn has a binomial distribution with parameters n and p is small, then Sn is approximately Poisson with parameter np. Let's do an example of applying this theorem before we get to a proof. So suppose that we roll 2 dice 12 times and let D be the number of times a double 6 appears. So each trial, we're rolling 2 dice, and then we do it 12 times, and we're counting the number of times we get 2 6s. Well, this has a binomial distribution, right? Because you're doing these independent events, so you're doing it n equals 12 times, right? So this is a binomial distribution where n is 12, and what's p? The probability that you get 2 6s, well, that's 1 over 36, right? So what this is saying is that the probability that D is K is approximately Poisson with parameter n times p, which is 1 over 3. Well, what does that mean? So that means that the probability that D is K is approximately e to the minus lambda. So lambda is np, right? That's 1/3. That's how we get this 1/3. So the probability that D is K is approximately Poisson with parameter lambda, so it's approximately e to the minus 1/3 times lambda, that's 1/3, to the k factorial, lambda to the k over k factorial. So let's compare the actual exact answers for k equals 0, 1, and 2. So for k equals 0, the exact answer, well, exactly, it's a binomial, right? So it's n choose k, that's n choose 0, that's 1. So the probability that D is 0 is 1 times p, which is 1 over 36 to the 0 power, times 35 over 36 to the 12th power. And that ends up being approximately 0.7132. Well, that's actually not, right? The exact answer then is 3536 to the 12th power. That's approximately 0.7132. If you use the Poisson approximation, then you're just plugging in k equals 0 in here. So we get that the probability that D is 0 is approximately e to the minus 1/3 times 1 over 3 to the 0 power is 1, over 0 factorial is 1. E to the minus 1/3 is approximately 0.7165. So we see that we get, right, to 2 decimal places, we actually get the correct thing. right? We get 0.71 to 2 decimal places either way. So a pretty good approximation. What about k equals 1? Well, we just do the same thing, right? The exact answer is that the probability that d is 1 is equal to, so n is 12. So 12 choose 1 is 12. And then the probability is 1/3 to the first power, and then 2/3, 1 over 36, sorry, and then 35 over 36 to the 11th power. And that ends up being approximately 0.2445. And if you use the Poisson approximation, the probability that d is 1 is approximately e to the minus 1/3 times lambda to the first power over 1, and then this is approximately 0.2388. So still pretty good. I mean, if you round these to the nearest hundredth, you get the correct thing. You get the same thing. And if you do k equals 2, let's just do one more, the exact answer is, well, the probability that d is 2 is 12 choose 2 times 1 over 36 to the second power times 35 over 36 to the 10th power. And 12, okay, let's just write down what you, so it's 12 times 11 over 2, right? Times 1 over 36 squared times 35 over 36 to the 10th power. And that ends up being approximately 0.0384. And the probability, so if you use the approximation, the probability that d is 2 is approximately e to the minus 1/3, 1/3 squared over 2 factorial, which is 2. And then this ends up being approximately 0.0398. So a good approximation. Okay. And as you can see, it's easier to calculate the Poisson approximation than the binomial, than the exact answer. Okay, now let's look at a proof of the theorem. Now that we have an idea of how to apply the theorem. So the first thing we need, the first fact is this lemma, which is just the standard calculus fact, which is that if you have a bunch of numbers lambda n that approaches lambda, okay, then the limit as n goes to infinity, so in other words, right, what this is saying is if the limit as n goes to infinity of lambda n is lambda, that's what I'm saying, then the limit as n goes to infinity of 1 minus lambda sub n over n to the nth power is equal to e to the minus lambda. That's a very standard calculus fact, so I'm not going to go over this. You basically use L'Hopital's rule to do this. Okay, so I'm just going to skip it. And using this result, how can we prove the result? Well, let's prove the theorem when k is equal to 0. So what is the theorem saying when k is equal to 0? Let's see. We want to show that the probability that Sn is 0 approaches e to the minus lambda. Right? Well, the probability that sub n is 0 is n choose 0, which is 1, times p sub n to the 0 power, which is 1, times 1 minus p sub n to the nth power. And the way we defined well, let's go back up here. Let's see. Let's define lambda sub n to be n times p sub n. So then your lambda sub n's are approaching lambda. Okay. So if lambda sub n is n times p sub n, then p sub n is equal to lambda sub n over n, right? So this probability is 1 minus lambda sub n over n to the n power, and we know that that approaches e to the minus lambda as n goes to infinity, which is exactly equal to what you get with the Poisson distribution. So that's by the lemma, right? And that proves the statement for k equals 0. Now when k is greater than 0, we have that the probability that the probability of s sub n being k is equal to n choose k times p sub n to the k power times 1 minus p sub n to the n minus k power. And that, in terms of our lambda, is n choose k times lambda sub n. I'll just make it clear that this is subscript. Lambda sub n over n to the k power times 1 minus lambda sub n over n to the n minus k power. Now let's write out the n choose k, right? That's n factorial over k factorial times n minus k factorial. When you write out n factorial over n minus k factorial, you get n times n minus 1 dot 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 up to n minus k plus 1. So you have that over k factorial, and then you have lambda sub n to the k over n to the k power, and then you have 1 minus lambda sub n over n to the n power times 1 minus lambda sub n over n to the minus k power. Okay, and we need to find the limit as n goes to infinity. Well, I can actually rearrange this. Let's move. Well, the k factorial is not relevant, right? It doesn't depend on n. So we can just move the k factorial out, and then let's move the n to the k to be under the numerator there. So you're going to get 1 over k factorial times n over n times n minus 1 over n times dot 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 n minus k plus 1 over n. So notice when we're doing this that we actually have k terms that are being multiplied. Okay, and then you have lambda sub n to the k factorial times 1 minus lambda sub n over n to the n factorial times 1 minus lambda sub n over n to the minus k power. So what happens when n goes to infinity? Well, each of these terms in the product are going to approach 1 as n goes to infinity. Right? Because k is a fixed constant here. So, okay, so those just go to 1, and then the lambda sub n, remember the lambda sub n's by hypothesis are approaching lambda. So that's going to approach lambda to the k power. And then what about the 1 minus lambda sub n over n to the nth power? Well, as we've stated in the lemma, that approaches e to the minus lambda. So that's going to approach e to the minus lambda. And then what about the 1 minus lambda sub n over n to the minus k power? Well, k is fixed, right? This constant is, the exponent is not changing as n changes. And the lambda sub n the lambda sub n's are changing, but the lambda sub n's are approaching lambda. And the denominator n is approaching infinity. So the thing inside the parentheses approaches 1. So this term is approaching 1 to the minus k, which is 1. So that's going to go to 1 as n goes to infinity. And so the limit, okay, so the limit of this what did I use? S sub n equals k is going to be 1 over k factorial times lambda to the k power times e to the minus lambda, which is exactly the Poisson thing, right? It's e to the minus lambda times lambda to the k over k factorial, which is what you get from the Poisson distribution. So that's the proof of the theorem. Okay, so that explains why the Poisson distribution is useful. It's used, for instance, as a model for the number of typos per page in a book. It could be used for approximating the number of traffic accidents in a day. Okay, so in this video, what we did was we reviewed the Poisson distribution and the binomial distribution, and then we proved the theorem that if you have a bunch of random variables, S sub n, with binomial distribution with parameters n and p sub n, and n times p sub n approaches some number lambda, then the probability that S sub n equals k as n goes to infinity is approximately, well, as n goes to infinity, the limit is equal to e to the minus lambda times lambda to k factorial, e to the minus lambda times lambda to the k over k factorial. That's the theorem. And then the way to think about this is that when n is really large, then S sub n is approximately Poisson n times p. Okay. So in the way we're thinking about it, I mean, the theorem, you only require the p sub n's to be such that n times p sub n approaches lambda, right? So you can have different lambda sub n's. But in practice, like in the example we did, the p sub n is just equal to p the entire time. Okay, thanks.